Okay, so we're looking at applications of differential equations. We're going to look at our first example. We're given the velocity of a particle dx dt, where x is the displacement, and we're told initially the displacement is 3 meters. Okay, so we've got to find the equation for displacement in exact form. So what do we know? Well, we know that initially, so t equals 0, x equals 3, and we can also work out the velocity dx dt by subbing in x equals 3 into 4x minus 1. So if we do that, we get 11 meters per second. All right, and what does the question want us to do? It wants us to find the displacement equation x of t. Okay, so calling this part A, we are going to first look at separating the variables. So you're told that dx dt is equal to 4x minus 1. So let's see what we can do to separate the variables there. All right, so starting with flipping, we're going to flip the derivative. So dt dx equals 1 on 4x minus 1. And then we're going to have dt equals 1 on 4x minus 1 dx. Okay, now we've separated the variables, we can integrate. So just put your integral sign there. And now integral of dt, think of this as just a 1 being there. There's a 1. So that's going to be t equals, it'll be the log of the absolute value of 4x minus 1, and you're going to need a quarter out the front, and we can put a plus c there. I just put the plus c, actually I'll put the plus c here, I've got the room, plus c. Okay, so next, what if I multiply everything by 4? So 4t is equal to the log of the absolute value of 4x minus 1 plus 4c, and put everything onto one side, not everything, 4c and log of absolute value of 4x minus 1. Okay. Now, if I raise both sides to the power of, if I put apply the exponential function to both sides, so we're going to go e to the 4t minus 4c is equal to e to the log of the absolute value of 4x minus 1. Okay, now let's write this as e to the minus 4c times by e to the 4t equals, and this will just be absolute value of 4x minus 1. Now, to get rid of the absolute value signs, we are just going to put a plus and minus sign over here. Plus, minus. Good. Okay, now, to make this a bit easier for ourselves, we're going to say that, let's change colour here for a minute. Okay, so we'll say that this here is just a constant. Let's call that a. So now we've got a e to the 4t is equal to 4x minus 1. Okay, so from there, now we could work out what a is at this stage, couldn't we? Because we know the initial conditions. The initial conditions come back here. T is 0, x is 3. So if we come back to the initial conditions, I'll put in t equals 0. So you're going to just get a then. And x equals 3, so a equals 11. So therefore we can say 11 e to the 4t is equal to 4x minus 1. And that's going to give you 4x is equal to 1 plus 11 e to the 4t. And can we squeeze it in down the bottom? I think we can. So that's going to give us x equals a quarter plus 11 on 4 e to the 4t. So there's our displacement equation, which is exactly what we wanted. So we found that in exact form. Right, part B, it says find the exact displacement after 5 seconds. Okay, so let's have a look at that. So we could come over here now and okay, so for part B now, we've got our displacement equation just up the top of the page there. So we're just going to now sub in x equals 5 into that equation. Sorry, t equals 5. So sub in t equals 5. So it's going to give you x is equal to 1 quarter plus 11 on 4 e to the 20. Okay, and you could factorize that if you wanted to. Take out a quarter as the common factor, but that is the exact displacement after t equals 5 seconds. Okay, what about part C? Part C says find the time when displacement is 10 meters. Okay, so we've got to find t when x equals 10. Okay, so let's do that. So it's going to sub in x equals 10, so you're going to get 10 is equal to a quarter plus 11 on 4 e to the 4t. Okay. Now let's get rid of those fractions. Times everything by 4. You'll get 40 equal to 1 plus 11 e to the 4t. And then that'll be 39 equals 11 e to the 4t. And 39 on 11 equals e to the 4t. And we'll keep going. We'll take the log of both sides. So we got the log of 39 on 11. And the log of e to the 4t will just be 4t. So then we get t is equal to 1 quarter log 39 on 11. Okay, so and that is approximately equal to 0.32 seconds. Okay, and that all right. So that's that first question done. All right. Now let's have a look at exponential growth. Okay, so exponential growth. Well, population is an example of exponential growth. And in general terms, exponential growth describes the growth of a quantity at a faster and faster rate over time. So you can see here on the graph, the curve is getting steeper and steeper and steeper. So that's an example of exponential growth. Now, as a function increases, the rate of change is increasing. So as the curve gets steeper, the gradient is becoming steeper. So that means the derivative is also increasing for exponential growth. So as you can see then, as q increases, dq dt also increases. Okay, now what about getting an equation for this? Okay, we know that we've got e to the kx is like is a possibility that there's an exponential equation. Or we could say Q for quantity is equal to e to the kt. However, both those equations have a y-intercept of 1, and this will not always be 1. What will it be? It'll be something else. So we can't use e to the kt, so we need a general case. So we'll say, look, let's just say you had a y-intercept of a. So there we go. Let's call that a, the y-intercept of a. That means a general equation for exponential growth could be q equals a to the kt. Okay, this one here. That means the y-intercept can vary according to the situation. Now, let's have a look at the derivative of an exponential growth function. So if I differentiate q with respect to time, I get to q dt equals ae to the kt times k. And this here, it's just q, isn't it? If you look. So I can replace ae to the kt with q. So I can write dq dt is q times k, or just kq. Okay, so for exponential growth, what can we say? Well, there's the equation for exponential growth, and here's its matching differential equation. Also, when t is 0, q is a. So a is the initial quantity. All right, so for exponential growth, a will be the initial quantity. K is also called the growth constant and can be expressed as a decimal fractional percentage. And what else we can say is that the gradient function dq dt equals kq is always positive for exponential growth. If it's always positive, that means k must be 0. Okay. All right. Further discussion. Now, what does dq dt equals kq mean? It means the rate of change of q is proportional to itself. So the rate of change of q is proportional to itself. Okay, this means that at any instant in time, dq dt will be the value of k multiplied by the population or the size of that quantity at that instant. So let's have a look at what that means. What does dq dt equals kq mean? Well, if you look at the exponential growth here, you can see at t1, the quantity is q1. So to actually find the derivative or the slope of the tangent at that point, all you need to know is the growth constant k. So if I take k and multiply it by q1 when t equals t1, that gives me the value of the derivative. So as long as you know the growth constant, you just have to find what the population is at that instant, and then you can determine the instantaneous rate of change. Okay, so dq dt will always be a percentage of the population at that time. Well, how come that's so? Well, because dq dt equals k times q. So since k can be a percentage, let's just say k was 2%, 0.02. So that's saying the derivative is a percentage of the population at a particular instant in time. Okay, so let's have a look at this from a table of values perspective. Here's a exponential equation, p equals 80e to the 0.02t. Now, without doing any derivatives, we can calculate what the derivative will be at a particular moment in time. So at t equals 0, now we know that what k is, don't we? We can see that the growth constant k equals 0.02. So all I've got to do is multiply that by the population at that time, and that gives me the value of the derivative at that moment in time. So if I go 80 times by 0.02, that's going to give me 1.6. Right? If I go 97.71 times 0.02. That means which we get 1.9542. That means at that instant in time, at t equals 10 seconds, the value of the derivative is 1.9542. And we can keep going with that. So let's go 119.35 times 0.02. It's going to be 2.387. Now, what you should notice is that the rate of change of the derivative is increasing, isn't it? That makes sense because the graph is getting steeper and steeper and steeper, so the value of the derivative at different moments in time should be getting larger. Okay, so we'll just do one more. So I'll take 145.77, multiply that by 0.02. That gives me the value of the derivative at that point, which is 2.9154. Okay, and you can do the other cells in the table if you so wish. Okay, now what about exponential decay? Well, one thing to mention about that is with exponential decay, we also have this equation to consider. Q equals A e to the kt. The difference here with exponential decay is that you're going to have k is negative because the quantity is decreasing. Okay, so you can see here, the curve here is not actually getting steeper, it's flattening out. And it's approaching, the slope of the curve will be approaching 0, won't it? Because you've got your asymptote there at y equals 0, if you like, or at q equals 0. So the quantity is decreasing at a decreasing rate. It's at a decreasing rate because it's flattening out. So you can see that in the table of values here. Here's an equation. Whoops. And we're using that equation there to complete the table of values. So there's my equation. And I've used that to complete the table of values. Now, have a look at the derivative. Now, we know that the slope of the curve is approaching 0 as t approaches infinity. So you can see this is getting closer and closer to 0. But you can also see the rate of change is also decreasing, isn't it? So even though numerically we're increasing, if you look at this from an absolute value point of view, like the size of the rate of change, the rate of change is slowing down, isn't it? So at t equals 20, the rate of change is almost 0, right? So that's something to be aware of. Okay, so for exponential decay, we've got the same equation, and the differential equation is the same. Difference is that k is less than 0 for exponential decay. Now, A will always be the initial quantity, so up here on your exponential decay graph, A is there, that's your initial quantity. Now, when exponential decay occurs, this means the death rate, if you like, if its population is higher than the birth rate. Okay, so let's have a look at this example. The population P of the country town is growing over t years according to the equation dp dt equals 0.024p. Okay, so this is exponential growth. So without too much thinking, we know that this is going to be of the form P equals A e to the kt, but we're going to derive that equation from scratch. So solve this equation given that the initial population is 35,000. So if you look at, so let's do part A now. So initially, so t equals 0, population is 35,000. And we can do separation of variables again for this one. So let's start off by flipping the derivative. That's going to make things a bit easier to do. So we're going to go dt dp equals 0.024p. And then once we've done that, we can now separate the variables. So we're going to have dp on one side. So I'll go dt equals 0.024p, and then let's integrate with the integral sign there. Okay, don't forget there's a 1. So it's going to be t equals. Now, if we integrate the right-hand side, and I think I've made a mistake there. I have, yes. Okay, let's just rub that out. When I flipped, I didn't flip the right-hand side. Okay, let's just fix it up. Okay, so flipping the right-hand side, I'll have 1 over 0.024p. That's better. Okay, so when I come to integrate, I should have this expression 1 over 0.024p, and then make sure you got the dp there. Okay, that's better. All right, so if I integrate 1 with respect to t, I get t, and if I integrate the other side with respect to p, we'll think of this, I'm going to have got my constant there, 1 over 0.024, and then that'll be log of p. Why not? P's got to be positive. Okay, so log of p for absolute value. Now you could say that p is a population, so we don't need the absolute value sign. That's true. So let's just get rid of the absolute value sign there. Okay, so because we know p is positive, no problem there. All right, now from there, I've got to make sure I've also added a c there because I've integrated. I can now put the constant on the other side. And in fact, before I do that, actually I'll do that. And then I've got still on the other side, I've got 1 over 0.024, and then log of p. Okay, so at this stage, we are going to multiply both sides by 0.024. So I'll get 0.024 outside of t minus c is equal to log of p. Now, from here, I'm going to raise both sides to, or apply the exponential function to both sides. So I'm going to get e to the 0.024 t minus c equals, now e to the log p is just going to be p. Okay, now from here, I'm going to split this up. E to the 0.024t times by e to the 0.024c with a minus equals p. Okay, now we can replace the c, the expression containing the c, or the term containing the c, with just an a. So you can say, well, that's equal to a e to the 0.024t equals p, right? And just make the qualification that a is just some constant e to the minus 0.024c. Okay, good. Now we've got to find out what a is, and we are given some information about that, because if you go back to the top there, we're told that t is 0 and p is 35,000. So if I now say initially, using initial conditions, so t is 0 and a is 35,000, that's going to then allow me to say, well, 35,000 is equal to a. So therefore, p is equal to 35,000 e to 0.024t. All right, and we knew that's how the equation was going to look because we knew from the beginning, if you look back here, that's the equation that we knew we were going to end up with. So all we did really was we found what k was. So A was and k. Okay, part B says find the population after 10 years. Okay, so if we're looking at part B now. All right, so part B. Population after 10 years. All right, so we're just going to sub in t equals 10. E to the 0.024 times 10. And let's see what that equals. So 35,000 times E to the 0.2444. And that'll be, say, 9, 4 to the nearest. There's people there. Okay. All right, good. So that's part B done. Now looking at part C. Okay, part C. All right. All right, that was part 1. So actually part 2. Part 2 says find the rate at which the population is growing after 10 years. Okay. So if you call this part 1, now we're going to use the differential equation for this. That's part I. Now for part 2 there, now I need to know what the population is after 10 years, which I've just worked out here, approximately. And I know that the differential equation dp dt is equal to 0.024. 0.024. Just that's not a 6 there, that should be a 0. 0.024 times by P. So if I want to know what the rate of change after 10 years, and I've just got to go 0.024 times by the population. Well, I'm actually going to use the exact figure from the calculator. So the exact figure from the calculator would be 35,000 e to the 0.24. Okay, that's will give me a more precise answer. So put that in. Should get 1,067.8. And it does say, doesn't really say how many decimal places, but we'll just do it to 1. Okay, so we could say it's approximately 1,000. It's growing at the rate of, say, approximately 1,068 people per year. Okay, that's what the growth rate is. All right, now, we've done that example. Let's have a look at something called Newton's law of cooling. So, Newton's law of cooling, here it is. So Newton's law of cooling states that a rate at which a body loses heat to its surroundings is proportional to the difference between its temperature and that of the surrounding medium. This is an example of exponential decay. All right, so first of all, let the temperature of the object be T and the temperature of the surrounding medium be M, where M is constant. For example, like room temperature. So if we're going to say that the rate of change, right, is proportional to the difference, right? So if you look at the very top part there, it says The body loses heat to its surroundings. The rate at which it does is proportional to the difference between its temperature and that of the surrounding medium. So this is the equation we can write. We can say that the rate of change, right, is proportional to the difference between the temperature of the object and the surrounding medium. Okay, so that's what this means mathematically. In other words, we can write this down as a differential equation, dt equals k brackets t minus m, where k and m are constants. Okay, now the general solution to this equation is this one. So it looks very similar to what we had before. We just got an extra constant. The initial temperature is m plus a, because when you put t equals 0, you get m plus a. Now, what does the graph of this look like? Let's have a look. So initial quantity is m plus a, and you can see here that as t approaches infinity, you'll be approaching m. So you've got to asymptote at y equals m there. Okay, and this is exponential to k, so you've got k less than 0. Now let's have a look at a proof of this formula. Okay, so you've got dt equals k brackets t minus m. Now we can write that, so obviously dt can be written as t dashed of t, and then we can make k the subject of the formula. Okay, so if I've got the t terms on the left side, I can now integrate both sides with respect to t. Now that gives me the log of the absolute value of t minus m equals to kt plus c. Now remember the formula that we used to integrate to get that result. Now, if I apply the exponential function to both sides of the equation, the log part will disappear, leaves me with the absolute value t minus m. And I've got e to the kt plus c on the left-hand side. Now I can split that up with e to the c times e to the kt. And to compensate for the absolute value sign, I'm just going to get rid of that and put the plus or minus sign there. Now, I can replace this with a constant a, can't I? I can say that's just some constant. So I can now write down a e to the kt equals t minus m, and that gives me the solution to the differential equation t equals a to the kt plus m. Okay, so if t has a rate of change proportional to the difference between t and m, then we can write this equation down. And the general solution to that equation is this, where a is a constant and the initial temperature is m plus a. Okay, now Newton's law of cooling is sometimes written like this. dt equals k t minus t1. And let's have a look at our first example. Now you've got an object that's heated to 320 degrees Celsius and left to cool. The temperature in the room is 26 degrees Celsius. If the temperature of the object is down to 290 degrees Celsius after 10 minutes, find its temperature after 30 minutes. Okay, so let's have a look at the solution for this. So for part A, we're going to write down that dt, that's our differential equation, equals k outside of t minus t1, Newton's law of cooling. Now, t1, we know the surrounding medium is 26 degrees Celsius, so that's t1. So you can write down that dt equals k outside of t minus 26. Okay, now we're going to do separation of variables on this. And before we do that, we should say, what are we trying to find here? We know that the other things we know is that t equals 290 when t equals 10. Yep. And we've got to find the temperature T, right, when T equals 30. Okay, so that's what we're going to do. All right, so that means we need a formula for T. So we're going to do it from the differential equation. So let's do separation of variables. So I'm going to have dt equals k outside of t minus 26 times dt, and then dt, scroll it up a little bit, dt over t minus 26 is equal to k dt. The good thing is I can now integrate, put the integral signs in there. Okay, so that's going to give me, think of this as 1, look a little 1 there in the numerator. I'm going to get log of the absolute value of t minus 26 is equal to k t plus some constant c. Okay, I'm going to apply the exponential function to both sides here. So it's just going to give me absolute value of t minus 26 is equal to e to the kt plus c. All right, so that's going to give me absolute value of t minus 26 equals e to the c times e to the kt. And then I'll get rid of the absolute value signs and say, look, t minus 26 equals plus or minus e to the c and e to the kt. Now, that is just a constant. So I'm just going to say t minus 26 equals a e to the kt, where a equals plus or minus e to the c. Okay, so almost there. Now that's going to give us t equals 26 plus a e to the kt. All right. Now we need to know what a is. So we've got some initial conditions here, and the initial conditions are t equals 0. Yep, so we know that t equals 0 and capital T is 320. So I can say 320 is equal to 26 plus A. Right, so A is 294. Good. Okay, so that means our equation can be updated. So we're going to have T equals 26 plus 294 e to the kt. Okay, now what about k? We need to know what k is. So to find k, let's change colours here. Here we go. To find k, we're going to use the other condition we know. What's the other condition that we know? We know that when t equals 10, we know that capital T is 290. So I can go, well, 290 equals 26 plus 294 e to the 10k. Okay, so take 26 from both sides, you're going to get 264 equals 294 e to the 10k. And just coming up here now, yeah, I'll try and write it over here. So, all right, so I'll just draw a little line, dividing line there. So the next line will be 264 on 294 is equal to e to the 10k. Now that's going to be 44 and 49. 44 on 49. And that's equal to e to the 10k. Now, you apply the log function to both sides. So you're going to get log of 44 on 49 equals 10k. So k is equal to 1/10 log 44 on 49, which is approximately equal to minus 0.0108. Now, what I would do is I'll put the exact value into your calculator. So if you use the following sequence of buttons, if you go press Shift, right, Shift, then you press the STO feature. STO stands for store. The STO feature is just above the RCL key, and then you press A, and A is just above the minus key, which the minus key in brackets. Okay, now that will put 1/10 log 44 and 49, the exact value, into the memory location A, which we'll use a bit later. Okay, now part B. Let's look at part B now. So part B, what does that say? Part B says, show that the final temperature of the object is 26 degrees Celsius. All right, now we have equation T equals 26 plus 294 e to the minus kt. We already found out k. I've already written it down, so I'll just leave it as k. Now I could write this down as 26 plus 294 on e to the kt. Now, as t approaches infinity, this term here, 294 on e to the kt, that will approach 0, won't it? Because the denominator will approach infinity. So that means t will approach 26 plus 0. So that means the temperature, the final temperature of the object as t approaching infinity will be t equals 26 degrees Celsius. Okay. All right, so we've got one last bit to do called the logistic equation. Now, by the way, I should have gone back here. If you wanted to reuse this value, so just that value that you put in there into memory bank A, if you ever want to use it in a calculation, you just press the RCL key, RCL, right? And then that stands for recall. Then you press alpha. Right, alpha because you're going to access the letter A, and then you press A. You can use that in calculation. So if you go RCL alpha A equals, and then press the equals sign after that, you should get the exact value, well, not the exact value, but you'll get the value of K filled across your screen. Okay, so let's have a look at the last bit, the logistic equation. Okay, so now this is a more general differential equation, and it's used for modeling and predicting results in biology, economics, and other areas. This is it. Here's your logistic equation. Okay, where n is the limiting condition or carrying capacity. So sometimes the logistic equation is written in different forms. So this could be another way of seeing the logistic equation. And K is your limiting condition. Now, what's so special about this? Well, unlike an exponential curve that increases forever, this equation is more realistic because for population growth, since lack of food and other resources can restrict population to a maximum level. So if you have a look at it, if your population is increasing exponentially, but then it's limited to, it can't grow forever because you're limited by its resources. So eventually the population will start flattening out depending on the limiting condition of the resources. Okay, so this is probably a more realistic equation to use for modelling populations. Having said that, the world is growing at an exponential rate. The population is certainly not approaching a limit. Now, let's have a look at this first question. Josh sets up a new salmon farm with 250 fish. The differential equation for P, the population of fish is given by dp dt, this equation here. We've got to show that this is true. Okay, so you know that with a show that question, you start with the one side and show it's equal to the other side. So let's have a look. Here's my working out space. So I'm trusting that you've printed these notes out. All right, so we are going to look at the right-hand side first. So let's have a look at the right-hand side. So the right-hand side is equal to 5 on 12 brackets 1 on P plus 1 on 1,000 minus P. Okay, now if you look at the left-hand side, we do want to have that 1,000 minus P somewhere in our answer. So first thing we're going to do is put everything over one denominator. Okay, so that's going to be 1,000 minus P plus P all over P and 1,000 minus P. Okay, good. All right, so the numerator tied us up nicely. So now we've got 5 over 12, and then we've got just 1,000 on the top line, and then P brackets 1,000 minus P on the bottom. Okay. Now, that is going to give us, to make it a little bit simpler, we'll just multiply the two fractions together. We'll have 5,000 over 12p brackets 1,000 minus p. Okay. Alrighty. So from there, how are we going to get 1 for the numerator? Well, I'm just going to put it there. So I'm just going to go, well, this is just 1 over p outside of 1,000 minus p multiplied by, now let's do the reciprocal. So we're just going to go 1 over 12 on 5,000, because the reciprocal of 12 on 5,000 is just 5,000 on 12, isn't it? Now, you can work that out. So that's going to be 1 over, close bracket here, 1 over p outside of 1,000 minus p times by, now what's 1 over 12 over 5, 12 over 5,000? Well, let's work it out. 12 divided by 5,000. Oh, it's 1 over, close bracket there, that's 1 over 0.0024. Okay, so we've pretty much got our answer there. So that's equal to 1 over 0.0024p outside of 1,000 minus p. There we go. Okay, so and that is equal to the left-hand side. Done. All right, now part B. Let's go back to part B now. So for part B, going back up here, okay, so let's use the result in part A to show that the salmon population is given by this. Now you can see the exponential in this. So that means we're going to have to do some sort of separation of variables here. So let's have a look at that. So, okay, so some separation of variables. We're going to use that given result. So here we go. So we've got part B there. All right. So we're given, we know that this is true, dp dt. Now we've got to use separation of variables to get the exponential result in there. So 0.0024p outside of 1000 minus p. Okay. So what can we do there? Well, what we can do is we can replace the expression there. So, all right, so first thing I'm going to do is integrate. Okay, let me just pause the video for a minute. Okay. Okay, so coming back to separation of variables, we're going to put the, we'll just multiply, I think, dp equals 0.0024p outside of 1000 minus p dt, and then dividing through, we're going to get dp over, think of this as 1 dp, 0.0024 p outside of 1000 minus p. Okay, and that is equal to dt. So now it says use the result. Now we are going to use the result, but first we're going to put an integral sign on both sides. Okay, so let's have a look at how we're going to use the result. Well, now we can replace that reciprocal function in the first integral, and we can replace it with 5 over 12 outside of 1 over p plus 1 over 1000 minus p close bracket dp, and then the right hand side is just going to be t plus c. Okay, so for our next bit we will integrate. So we're going to have 5 over 12 outside of will be the log of p, and then minus the log of 1000 minus p. We can put that in absolute value. Absolute value, that's fine. And that's equal to t plus c. Okay, so from there, we could say that this is 5 over 12 log of p, using our log laws, p over 1000 minus p, absolute value, equals T plus C. Okay, so from there, we are going to get rid of the 5/12 on the other side. So we're going to go, this is log absolute value, P over 1000 minus P equals 12 over 5 brackets T plus C. Okay, so we're going to apply the exponential function to both sides now. If I apply the exponential function to the log, I just get P over 1000 minus P, absolute value, equals, and E, we'll make this 2.4, 12 over 5 is 2.4, and that's T plus C. Okay, so it's going to give us still absolute value, P over 1000 minus P, absolute value, which is equal to, now we'll split this up. We're going to make this as E to the 2.4C times by E to the 2.4T. Now, to get rid of the absolute value sign, we're just going to put a plus or minus on the other side. So P over 1000 minus P is equal to plus or minus E to the 2.4C and E to the 2.4T. Okay, this is just a constant. So we can write down that P over 1000 minus P is equal to A E to the 2.4T. Okay, now, so looking good so far. We've got the A there. Now let's have a look at what we can do with this equation. Now we could find out what A is because we do have some conditions given to us. So okay. All right, so what are our conditions? All right, so let's have a look. Let me just pause the video again for a minute. So let's look at my notes. Okay, so our initial conditions, just looking back at the notes, initial conditions were T equals 0 and population was 250. So we can use that to get what A is. So that's going to give me 250 over 750 is equal to A. So it's going to give me a third is equal to A. Okay, so that's good. All right. So what's our equation become now? So now we have P over 1000 minus P is equal to, now it's going to be 1/3, then E to the 2.4T should be, yes, E to the 2.4T. Okay, good. All right, so next step, we can get rid of that 1/3 there by putting this as 3P over 1000 minus P equals E to to the 2.4t. And we can take the reciprocal now, if you like. So if I flip both sides, I will have 1000 minus p over 3p equals 1 over e to the 2.4t. Okay, so where's the result that I've got to show? Okay. All right, so the next thing we can do is we can get our negative power, because we can say this is 1000 minus p over 3p equals e to the minus 2.4t. There's our negative power. And then from there, we can say 1000 minus p equals 3p e to the minus 2.4t. And then 1000 is equal to 3p e to the minus 2.4t plus p. Take out your common factor. You've got 1000 is equal to p outside of 3e to the minus 2.4t plus 1. Okay, and that's looking good. And then the last bit we just got to do is divide through. So you're going to get p equals 1 plus 3e to the minus 2.4t. Actually, that's not right, is it? So close. All right. We need the 1000 first. Okay. 1000 divided by 1 plus 3e to the minus 2.4t. Okay, that's it. All right, and the last bit we've got to do, part C. Okay, so for part C, it just says when t equals 2, work out the population of the fish. So sub in t equals 2, so t equals 2, population is 1000 divided by 1 plus 3e, and that'll be double that is minus 4.8. And work that out on the calculator. You should get 976 approximately. So let's put down that approximately 976 fish. All right, now the second part of the question says, what is the maximum possible population? Oh, sorry, after 5 years. So let's do 5 years. So when t is 5, well, same process. P equals 1000 divided by 1 plus 3e. Now, minus 2.4 times 5 is minus 12. Put that into your calculator and you should get approximately 1,000 fish. It's 999.98. So let's just say about 1,000 fish. Now the last part of the question says, what is the maximum possible population of fish? Okay, so we're looking at a limiting situation here. So if I look at D, now, what's my equation? P is equal to 1,000 over, now I'm going to write the equation as 1 plus 3 on E to the 2.4t, because as t approaches infinity, right, 3 on e to the 2.4 t will approach 0. Okay, so that means you're going to get 1,000 over 1 plus 0, which equals 1,000. So his maximum possible fish number is 1,000 fish. All right, so put the units there, fish. Okay, that completes the video. Okay, so you can now do exercise 1304.